Hi, today we're going to discuss a practice problem that is based on linear algebra, and it has an application on many of the machine learning algorithms that we're going to see throughout the class. So the goal of this specific problem is to formulate and solve a classification problem in which we would like to know whether an individual is diabetic or non-diabetic. And we're going to select two attributes that we know that might be related to diabetes, mainly two factors that actually cause diabetes. And these include the body mass index, BMI, which is noted in our case as variable D1, and the family of history of diabetes, which is denoted as variable D2. So we have, as per our example, we have training data from 3 individuals, samples X1, X2, and X3. And for those 3 individuals, we both know their attributes, meaning the BMI and the family history, as well as their outcome, meaning whether they're diabetic or non-diabetic. So sample X1 is a non-diabetic sample. This is the label for this specific participant. His or her BMI is 5, and he has 1 relative with diabetes. Sample X2 is non-diabetic with a BMI of 5 and 2 relatives with diabetes. And sample X3 is diabetic with a BMI of 30 and 3 relatives with diabetes. So in this problem, we are going to express this information in a vector notation. We are going to obtain a mathematical expression to classify between diabetic and non-diabetic individuals based on BMI and family history of diabetes. And finally, we are going to obtain a decision for an unknown person for whom we have the BMI and family history, but we do not know the diabetes outcome. So as part of part 1 of this exercise, we are going to consider a 2D representation space as shown in this screen. This 2D representation space, the x-axis corresponds to variable D1, which is the body mass index, and the y-axis corresponds to variable D2, which is the number of relatives with diabetes. So the first part of this question asks us to plot the 3 data points, X1, X2, and X3, on this 2D representation and write those in a vector notation. Let's go ahead and plot these 3 points on this 2D space. The first point, sample X1, is a non-diabetic participant. So this is the label, and the BMI is 5, and this person has 1 relative with diabetes. So we plot this sample whose X value is 5 and whose Y value is 1. Like that on this 2D representation space. And I'm just going to use this X to denote the non-diabetic class. And I'm going to use another sign to denote the diabetic class. And if I were to write X1 in a linear algebra notation form as part of a vector, it would be X1 equals 5, which is the first dimension, and 1, which is the second dimension. Similarly, for sample X2, the BMI is 5, and this person has 2 relatives with diabetes. Therefore, I go here and I plot another sample. Again, this sample is non-diabetic. Therefore, I preserve my notation with X for sample X2, whose vector is equal to 5, 2. Now we're going to the third sample, whose BMI is 30, and this person has 3 relatives with diabetes. 3 somewhere here. So we find point 30, 3. Now this time, because X3 is diabetic, I'm going to denote X3 with a circle here, and X3 equals to 30,3. If I wanted to put a small legend here, I could put a legend like that, where X denotes non-diabetic individuals, and this circle denotes diabetic individuals. If I wanted, I could have denoted that with a different color as well. So this pretty much takes care of this first part of this exercise. Now, the second part says that we would like to find a line that separates diabetic from non-diabetic individuals. This line, formally in machine learning, is called decision boundary. And we are interested in this because after we have this, we can actually get a decision for our entire space rather than only for these 3 points that we have. So this exercise actually gives that this line passes from points 30, 0, and 0,3. So it asks for us to plot the line in the above figure and find its equation. So we find 30, 0. We also find 0,3. We plot the corresponding line, somehow like that. So how do we find the equation of the line? All the way from calculus, we can find the slope of the line. So the slope of the line is 3 divided by 30, the distance between the vertical and the horizontal axis. So the slope is, and because the slope is negative, is minus 3 divided by 30 times x. And what I'm going to do this here, I'm just going to keep the axis notation. So instead of the typical xy notation, I'm going to preserve the notation that we have with d2 and d1. So this is d2 equals minus 3 over 30 d1, and then the intercept, which is on the y-axis at 3. Or otherwise, this line is d2 equals minus 1 over 10 d1 plus 3. And here again, this is the slope, and this is the intercept. Now, as part of 2b, using this line, we would like to form a classification function, which will decide whether a new sample X belongs to class 0 or class 1, the diabetic and non-diabetic class. For this, we will need to express F with a rule-based equation, like the example provided here. So how would we do this? If we inspect this figure, we see that samples that are on the right side of this line appear to be more the diabetic individuals. First of all, because we have sample X3 here on the right side of this line, which is diabetic. And we also have samples X1 and X2 on the left side of the line, which are non-diabetic. So having said that, a reasonable classification rule would be that whatever is on the right side of the line is a diabetic sample. And how do we express right and left in mathematical terms? Whatever is greater or less than 0. So if we were to put this down on an equation, we would say that a sample X belongs to class 1, which is the diabetic class, if it is on the right side of the line. D2 equals minus 1 over 10 D1 plus 3. Or if we were to put that in a function-based form, it would be that minus 3 plus 1 over 10 d1 plus d2 is greater than 0. And similarly, x would belong to class 0, which is the non-diabetic class, if it is on the left side of the line, and therefore d2 equals minus 1 over 10 d1 plus 3. I'm sorry, this is d2 is actually less because it's on the left side of the line. And here it should be greater because it is on the right side of the line. And if we were to write this further, this would be minus 3 plus 1 over 10 d1 plus d2 is less than 0. So this classification function, we can see from here that we have these equations here and these equations here. And this first part is very similar in both equations. This should be function f d1, d2. Therefore, our classification function would be f d1, d2 equals minus 3 plus 1 over 10 d1 plus d2. So if f of d1, d2 is greater than 0, then x belongs to class 1. Otherwise, if f of d1, d2 is less than 0, then x belongs to class 2, class 0. So that was question 2b. Basically, we formed a decision boundary. The decision boundary was actually being informed by our training data, x1, x2, and x3. And it was formed such that whatever is on the left side of the decision boundary belongs to one class, in this case, class 0, and whatever is on the right side belongs to class 1. We further, based on this decision boundary, we further got a classification function, this function f of d1, d2. So now, question 2c asks us to express the 3 given data points in a matrix notation, and we are being given this matrix B here. And we are simply set to substitute the values of x1, x2, and x3 in the above equation. So that's pretty simple. Actually, if we substitute that, this will be 1, 5, 1, 1, 5, 2, 1, 33. And the size of this matrix is 3 by 3. Here, we can see that this dimension corresponds to the number of samples. And this dimension here corresponds to the number of attributes or the number of features, class 1. And I'm saying class 1 because we have this here, this row column of ones, which we are going to explain in a little bit why it is there. So now what this question asks is to multiply D with the weight W, which is being given here. So to do that, we're just going to follow very simple linear algebra notations and operations. And we can multiply these two because this is a 3 by 3 array and this is a 3 by 1 vector. Therefore, if we do this multiplication, the result would be 3 over 2, 1 over 2, and 3. This is a 3 by 1 vector. And essentially, we see that this element here is less than 0. This element here, the second element of the vector, is less than 0. And the third element of the vector is greater than 0. So what do we observe here? First of all, these numbers, -3, 1 over 10, and 1, are very suspiciously similar to these three coefficients here, -3, 1 over 10, and this hidden one with which D2 is multiplied. So we can understand that these are some coefficients that are being multiplied with our variables of interest. In this case, our variables of interest are D1 and D2, meaning the BMI and the number of relatives with diabetic history. And we also have here, in this specific case, another hidden variable, which is just our bias, the constant of 1 by which all these equations are being added to. So essentially, this essentially what we can see is that if we have any vector x, which can be written 1, D1, and D2, and D1 here stands for the BMI, D2 stands for the number of relatives, and this one stands for the bias term. So if we multiply x by this weight, -3, 1 over 10, and 1, which we can say that this is a vector W, which is a vector of coefficients that correspond to the decision boundary, then what we have is that we have exactly the equation of the decision boundary that we have formed in the previous question here. So this decision boundary that we found here has this algebraic notation, but it also has this matrix vector notation here. And we can actually make this a little bit more consistent with the previous question. So this was the vector x that we had defined. And this whole thing here is the vector 1x. And why we did that, we added this one so that we can multiply this one by this -3, and that we can add our bias term. So finally, the last question of this exercise asks us to assume that we would like to find whether a person X4, whose BMI is 10 and has one relative with diabetes, is diabetic or not. So how would we write X4 in a vector notation? That's pretty simple. X4 would be 10, 1. And if we were to classify this person based on the rule decision that we found in 2b, this person would be basically, from this rule, we would have -3 plus 1 over 10 times 10, which is the first variable for this person, plus 1 times 1, which is the second variable for this person. This would be -1. -1 is less than 0. So going back to this rule here, since this f of D1, D2, in this case, f of X4 is less than 0, we understand that the person belongs to class 0, therefore the person is non-diabetic. We could have done this in a slightly different way. Instead of only having the two variables of x4, mainly BMI and number of relatives, we could have kept this vector notation for x4. In this way, we would have had 1, 10, 1. And we could have multiplied this vector by the vector W that we found in question 2C. The vector W was -3, 10, 1/10, and 1. Therefore, if we multiply our data vector with our weight vector, we would have found exactly the same thing. And we would have made exactly the same decision. So that is the end of the first part of this tutorial. And if you like this tutorial, please watch the next video for the second part of this tutorial. Thank you.